Hey guys, Brian here from Control System Lectures. In this video we're going to do something a little bit different. We're going to talk about humans, we're going to talk about robots, and hopefully have a little fun in the process. Have you ever counted how many different ways you can move your hands? Now, I'm not talking about how many different positions they can be in, but physically how many different ways you can bend it. For example, with your pointer finger, you have 3 knuckles, and so you can bend your finger 3 different ways in this direction. That's 3 degrees of freedom. Plus there's this sort of side-to-side wagging motion. And if you add up all your fingers and your palm and your wrist, you have upwards of 24 degrees of freedom. So it's no wonder that humans use their hands to do things like grip objects. Here I'm holding onto this object, I'm grasping it, and this is how I'm manipulating this object through space. This type of manipulation is called prehensile manipulation. Prehensile just means to grasp or to grip something. Now, if you've never heard the term prehensile manipulation when talking about human hands, you may have heard this when people are talking about like monkeys and their tails. For example, a monkey has a prehensile tail. It just means that it has a tail that can grip something like a tree and hang from it. So it makes sense that if you want to build a robot that has the same capability as a human, you want to build in the ability to do prehensile manipulation. Basically, you want to build a robot with hands. Recently, I was at the International Conference of Robotics and Automation, and there were a lot of examples of robots doing prehensile manipulation. These are robots that have pinchers and claws and things that look a lot like human hands. But humans do a lot of non-prehensile manipulation as well, and you may not realize that you're actually doing it. For example, if you get out of your car and you're holding a lot of stuff and you need to close your car door, you sometimes do it by just bumping it with your hip to close it. That's non-prehensile manipulation. Or if you're pushing something across your table with just your fingertips, that's non-prehensile manipulation. Also, if you're throwing a ball, this is a really complicated motion because it starts with prehensile, or gripping the ball, but as it's leaving your hand, the last thing it does is roll off your fingertips where you impart spin and the last little bit of direction change, and that is non-prehensile manipulation. So you would expect that in order for a robot to mimic the things that humans do, they would also need to be good at non-prehensile manipulation, and there was a fair amount of this at the conference as well. One in particular that caught my eye was the continuous manipulation of a ball rolling around what is called the butterfly robot. This particular robotic demonstration is done by Maxim Surov and his colleagues. You might look at this and think, this hardly looks like a robot to you. And the mechanisms aren't terribly impressive. It's really just a motor driving a shaft with this butterfly figure 8 on the end and a camera that can tell where the ball is. But it's not the mechanisms that are the impressive part. It's the algorithm that's driving it that's really revolutionary. In fact, they told me that this was the first time that this problem had ever been solved, and the first time that this was ever demonstrated in the United States. The reason this is so hard is because this problem can't be simplified or linearized at any point. It has to be solved in a non-linear fashion. Now, I'm not familiar enough with the mathematics behind it to explain it, but I did want to see if I could figure out how difficult of an accomplishment this was by repeating it myself. But not with me developing a robot to do it, with me as the human trying to accomplish that exact same feat. So I built this sort of human-powered replica of the butterfly robot. Whoa! That one actually wasn't that bad. But I may just be incompetent at doing this. Let's give it to somebody else and see how well they do. Human control systems are extremely complex and impressive. I mean, we can control non-linear systems really well, and we can adapt to changing environments. But we have a bandwidth, which is basically a range of frequencies that we can respond to. For example, you wouldn't expect to be able to control something moving faster than you are able to move your arm. This is driven mostly by our slow sensors and our big slow actuators. This is really easy to see by balancing a stick on the end of your finger. The longer the stick, the slower the dynamics of the system overall, and my hand is able to keep up and keep this thing balanced. But if we move to a smaller stick, the dynamics get a little bit faster because whenever it starts to fall, the angle that it travels in a certain amount of time is a larger angle, and it's harder to respond to that. And so balancing a smaller stick is a lot more difficult. And you can try this on your own. But this is just my hand-eye coordination control loop. There are other loops in the human body. There's tons of them. For example, another one is from my eyes to my foot. And I can demonstrate that by trying to balance this stick on my foot. And it's much harder. Not only is my leg doesn't have the degrees of freedom of my arm, it also just doesn't move as fast, and I haven't practiced it, so I'm a lot worse at it. So not only is the bandwidth of my hand-to-eye coordination different than my foot-to-eye coordination, bandwidth changes from one individual to another individual. And you can see this by getting sticks of a whole bunch of different lengths and going to your friends and seeing how small of a stick you can get and balance it on the tip of your finger versus other people in your group. And I bet you'll be able to find that if you just practice at it, you'll be able to get to smaller and smaller sticks, at least to a limit where you run out of bandwidth and you can't move your arm any faster. So I have a theory that the reason why this is so difficult for humans is because it's so small, and the reaction time of humans is limited by the ability to turn their wrist fast enough and to see what's going on. And the smaller something is, the less time you have to react to it. So I think the solution that will make this a little bit easier is to go much bigger. And that's what this is for. We're going to see if we're capable of doing continuous rolling motion but with a much bigger butterfly robot, and see if we can pull the dynamics into the bandwidth of the human control loop. Okay, let's tie all of this together. I mean, what does this have anything to do with building a more capable robot? Well, walking is a form of non-prehensile motion, manipulation, because we're not actually gripping the ground with our feet. And if you saw the DARPA robotic challenge recently, you might have seen some of the outtakes from some of the videos of a bunch of robots, bipedal robots, robots with two legs, falling down all over the place. And the reason is it's really hard to get a robot to balance on two legs and move at the exact same time. In fact, the way that a lot of them are doing it right now is that they move from one static, stable position to another static, stable position as they're walking, and they're keeping their center of mass above their feet. And you can imagine that if you had to walk like that, if you had to keep your center of mass constantly above your feet, it would be really slow, that you wouldn't be able to lean forward into motion and run, for example, or walk really quickly, or jump, or anything like that. So it's a really difficult problem to solve, and it's one that we still have a lot of work to do. Okay, we can demonstrate this really easily by looking at Boba here. Boba has 2 feet, he's bipedal, and he's standing on his own. And the reason is because I've balanced him so that his center of mass is directly over his feet. But he's not globally stable, because if I give him a little bit of a disturbance there, he just falls right over. So this is sort of the way that the robots are walking and moving right now, especially at the DARPA Robotic Challenge, where they are statically stable at any given point, but they don't respond very quickly or very efficiently to a lot of external disturbances. Now, if we had a robot that had feet that looked like this compass here, they don't have the big, large feet platform, so it's harder to get the center of mass directly over them. And no matter how hard I try, I won't be able to balance this. So if we wanted to be able to keep this upright, we would have to develop a walking robot that whenever the center of gravity moves outside of the feet, it needs to continuously move its feet underneath it. And this type of continuous motion to generate stability is very similar to the type of algorithm that Maxim Surov developed for the butterfly robot. In fact, his formalized approach to solving these types of problems could go to solving problems just like this, allowing robots to walk a lot faster and a lot more efficiently. If this type of research is something that interests you, figuring out a way to make robots run and walk better than they already do, check the description below and I've left some links to some interesting papers. Also, if you have any questions or comments on what I talked about, leave them in the section below and I'll try my best to answer them. Don't forget to subscribe so you don't miss any future videos, and thanks for watching.
You're just trying to give me stupid stuff to put it on the internet.
The internet doesn't care about stupid stuff.
I can't even tell if it's straight.
Just don't stab yourself in the eye.
That's just not going to work.
Yeah, let me see. You set this one up in the meantime. I think the nose is probably going to be easier. Maybe not. Forehead.
Hey, not bad. Must have a really light.